Hi, everyone. So the bottom line is that you need to be able to prove this conjecture, that the following is true for all positive integers n. That is for all n in the set of positive integers, z plus. P sub n, the statement P sub n, this is like a proposition, which states that the sum of the first n positive integers, 1 plus 2 plus 3 plus yah plus n, equals this fraction, n times the quantity n plus 1 all over 2, where the left-hand side is not in closed form, but the right-hand side is a closed form formula, which was obtained from combinatorial interpretations from methods 2 and 3. Now, bear in mind that we're trying to prove here infinitely many statements. How do you prove infinitely many statements? Because remember, P sub n gives us a different statement, technically, for each different positive integer n. So we want to prove infinitely many statements corresponding to the infinitely many positive integer values of n. How do you do that? Proving infinitely many statements? And when do you do it? Well, in quite a bit in higher math. Induction is commonly used in discrete math and in linear algebra, especially. For example, what if you want to prove something, a property is true for all square n by n matrices? Well, you want to show that it's true for 1 by 1 matrices, 2 by 2, 3 by 3, and so on, 100 by 100, and so on. So how in the world do you prove this statement if you're considering all these infinitely many cases? Also, if you want to prove a property for determinants of square matrices of various sizes. Also, induction is used in continuous mathematics. For example, in calculus, induction is used to prove integration formulas involving powers of or products of powers of trig functions. So for example, how do you integrate sine to the nth of x for high positive integer values of n? Induction is used as a method of proof in higher math. Now, what's the key idea behind induction? Well, you could think of it as climbing a ladder, as we mentioned before, all right? We can also think of it in terms of a domino image or analogy. So imagine this line of dominoes, a line, kind of a ray almost, of infinitely many dominoes. When are we guaranteed that each domino will eventually fall? Well, I hope you agree that eventually each domino will fall if we have the following holding true. If it's true that the first domino falls, and that corresponds to the basis step, so that means that this first domino gets tipped over, right? And then the fall of one domino guarantees the fall of the next domino. And this corresponds to what we call the inductive step. So if one domino falls, then we're guaranteed that the next domino will fall. If one falls, then two falls. If two falls, then three falls. If three falls, then four falls, and so forth. If a domino falls, it means that basically this statement is true for the corresponding value of n. So if one falls, that means that p sub 1 is true. If two falls, that means that p sub 2 is true. If three falls, p sub 3 is true, and so forth. Okay. By p sub 3 falling, we mean that this statement is true in the case of n equals 3, in which case we don't worry about this piece here. We're saying that 1 plus 2 plus 3 equals what you get when you plug in n equals 3. Bear in mind that even though this left-hand expression may seem to only make sense for reasonably large values of n, we assume that if n is small, it compresses. So if n is 1, then the whole left-hand side compresses down to just 1. So the expression compresses as necessary. So in order for each domino to eventually fall, we need the first domino to fall. And if one domino falls, then we have to be guaranteed that the next domino will fall. Now, if you agree that both of these happen, then you agree that each domino will fall eventually down the line. Now, of course, we need the first domino to fall. It's nice if these dominoes are stacked like this, but if the first domino is not falling, these dominoes might just be staying there. I mean, how are they going to fall? Am I going to yell at the dominoes, fall? Well, I don't know. Maybe nowadays with my breath, it might work, but but I think it would help for the first domino to fall. Okay. Now, that's not enough. I mean, if the first domino falls, right, that's not enough. Let's say this domino falls, domino one, okay? It could fall and then poop. It just kind of lies down there and it doesn't affect any of these other dominoes. So if domino one falls, it doesn't help much if we're not guaranteed that the next domino will fall, and then the next domino, and so forth. If these dominoes are too spread apart, then it doesn't matter very much that the first domino falls because you're not starting the chain reaction. We need the dominoes to be kind of close together to be able to see the chain reaction execute. That's basically the inductive step, the guarantee that if one domino falls, we're guaranteed that the next one will fall. So that's the idea of the domino image or analogy. The actual proof, which you need to know how to do, we're going to talk about in detail next.